The topic is proving triangles are similar using 3 similarity theorems. So if we start out with 2 angles of one triangle that are congruent to 2 angles of another triangle, angle A is congruent to angle D, and angle F is congruent to angle C, then that is enough to make those 2 triangles similar to one another by angle-angle similarity. So if you recall back when we were working with triangle congruence theorems, we had 5 theorems: side, 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 angle, side, hypotenuse, leg, angle, angle, side, and angle, side, angle. But there was never one that was called angle, 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 for good reason. That angle, angle theorem allows 2 triangles to have the same shape, but not necessarily the same size. The angle measures preserve the shape. So these 2 triangles are now similar to each other, and we have to be careful to name them correctly. So if we want to call the first triangle triangle ABC, then we have to make sure that we match up angle A with the angle that it was congruent to in the other triangle, D. Angle B with, there's no marking there, E, and then finally angle C with angle F, since they both have the double marks. So if 2 angles of one triangle are congruent to 2 angles of another, that's sufficient to prove that the triangles are similar. So for our first example, we're going to see if these 2 triangles are similar to each other or not. And I see that we have a 35-degree angle, angle T, and angle S is also 35. So by angles, one set of angles, that's not enough to make the triangles similar, but we can check the others. So when we notice that we have a 65-degree angle and an 85-degree angle, those are not congruent to each other. But if we add 65 to 35, we will get a even 100, and the angles of a triangle add up to 180. So if we take away 100, we should get 80 degrees. So this angle V is 80 degrees, whereas angle Q is 85 degrees. So no, they are not similar. So we don't need to write a similarity statement. But in our second set of triangles, we see a 25-degree angle congruent to a 25-degree angle. We know nothing at all about the sides. They're only angles that are being shown. And if we take 82 and add 25 to it, we get 107, and 180 minus the 107 gives us 73 degrees. So angle E is 73 degrees. Angle T is also 73 degrees. So we know that these 2 triangles are similar. So we're going to write a triangle similarity statement. We can choose any way we want to say that our names of our triangles. So we might call this triangle CED. Excuse me. So triangle CED would be similar to, I started with my smallest angle, I went to my medium size and my largest, so smallest, medium, large is going to be UTS by angle-angle similarity. In example 2, we aren't given any sides, we aren't given any angles whatsoever, but we are told by these arrows that we have 2 parallel lines. Well, anytime we have parallel lines cut by a transversal, our corresponding angles, same side, same position, have to be congruent to each other. Those are our parallel lines. This is our transversal. Likewise, angle L and angle PMN are also congruent since they're corresponding angles. And N, if we would think about those 2 triangles, a larger one and a smaller one, I'm not drawing this very well, I'm apologizing, they both triangles have angle N in them. And so, yes, these 2 triangles are similar by angle-angle similarity. We get triangle LNQ similar to triangle MNP. Again, the order matters when we're stating our similarity statements. Last example for this particular theorem, says I've got some parallel lines. I was given that angle R is congruent to angle U, but with these parallel lines cut by a transversal, if I trace the parallel lines, I trace the transversal that connects them, then I will have some alternate interior angles that are congruent to each other. So since SVR is congruent to URT, we have two pairs of angles. So by angle-angle similarity, we have triangle RUT similar to triangle. If I started with R, I have to start with V, so VRS. All right, a second way to prove triangles similar is to use the side-side-side similarity theorem. And that says that if the measures of the corresponding sides of two triangles are proportional, then the triangles have to be similar. So if NO, that distance between NO, is over QR, is proportional to the distance between OP and SR or RS, and that's proportional to the distance between NP or PN and QS, then these two triangles have to be similar. So triangle NOP, blue to red to orange, is similar to triangle, we're going to red, so QRS. So really watch to make sure that you're paying attention to reflections or rotations, and don't just assume that they're a translation and then made smaller or shrunk or larger, enlarged. All right, example 3 then says, let's use the triangle similarity, side-side-side similarity to make sure that these triangles are similar, and if they are, give a similarity statement. So remember the story of Goldilocks and the 3 bears? You had a papa bear, a mama bear, and a baby bear. Same idea here. You want to pay attention to your largest size. This would be the papa size, or the biggest, versus the papa on the other one, on the smaller triangle. The medium-sized side is the 12, so this would be mama, and 9 would be the mama, and the babies on both triangles are the 8 and the 6. So we want to set up the proportions accordingly. So my largest triangle's largest side over smallest triangle's largest side should be proportional to the medium size on the bigger triangle to the medium size on the smaller triangle, should be proportional to the baby on the big versus the baby on the small. So we could divide these in a calculator to see if they come out with the same decimal. We can say they both have a 4 in common, so 4/3. These two both have a 3 in common, 4/3. These two have a 2 in common. When we simplify, we get 4/3. And since 4/3 equals 4/3 equals 4/3, yes, they are similar. Triangle JKL, alphabetically, is similar to triangle J is the papa to the baby, so papa to baby means we use QPM. So they won't necessarily be alphabetical. You have to be careful to match things up by side-side-side similarity. All right, another example. These two triangles are now similar. We have a similarity statement, so this is like the converse. So we know the triangles are similar. We want to find the value of x that makes them similar. So you can decide how you want to set this up, but if I have a choice, I'm going to use x minus 2 over 3 times the quantity x minus 6 because it's simpler. And so GI, the x minus 2, should be proportional to JL. JL is the 30. As, now I'm going to pick two pieces that I can work with that don't have x's if I can help it. GH is to JK. So small triangle to small triangle, a small triangle to large triangle, x minus 2 to 30 as 5 is to 15. And now if we are cross multiplying, we make sure that we take the 15 times both the x and the negative 2, and the 5 times the 30. But we can also realize, hopefully, that if I'm eventually going to divide by 15 anyway, we might as well divide by 15 right now and have x minus 2 is equal to 5 times 30 divided by 15. 30 divided by 15 is 2. 2 times 5 is 10. So it simplifies math a little bit. We add a 2, and x is 12. That is the value of x that makes these two triangles similar to each other. Once again, paying attention to who our papa, mama, and baby, our largest, medium, and small size sides are. So in the first examples, we saw only angles. The second examples only had sides. In this third theorem, we have both sides and angles. And the key to it is if the two pairs of sides are proportional and the included angles are congruent, then the triangles are similar. So JK over GH has to be proportional to, get a better color here, JL over GI, and the angle between them has to be the angle that we're talking about, the included angle. And so then if that happens, triangle KJL is similar to triangle HGI. So let's see an example of that. If we're determining whether these are similar, we have to make sure that we have two sides and the included angle, the two sides proportional, the included angles are equal. So I see this angle 75 degrees is equal to this angle that's 75 degrees. But before I even bother to set up my proportions, I notice that one of the sides that includes that angle is 75, but I don't know the other one. So this is an angle with a side and then a side over here. That's not side angle side. So before I get too crazy about setting up proportions, I can immediately say not similar or not enough information, not applicable, however you want to say it, NA, because this doesn't follow a side angle side pattern. In our second example, though, we don't know that these lines are necessarily parallel, but we do have two triangles. We have a small triangle, I'm outlining in green, and I have a larger triangle that I am outlining in orange, and the angle K is being outlined by both of those. So angle K is in both triangles. And we do see the two sides that help make that angle in both triangles. So now we know that we could be working with a side angle side. So the green triangle has a side that is 8, but the orange triangle has a side that is a total of 10. And a second side, KN, that is a total of 15. And so 8 goes with 10 as 12 goes with 15. So we want to check, are these proportional? 8 and 10 both have a 2 in common, so that simplifies to 4/5. 12 and 15 both have a 3 in common. If we divide 12 by 3, we get 4, and 15 divided by 3 is 5. So yes, we have a side angle side similarity situation here where triangle MKN is similar to triangle LKP. And so there is your assignment.